Good morning, everyone. My name is Ming Wu from Erasmus Medical Center in Rotterdam. And today I'm going to present the work about the acoustical and optical spectroscopy of plaque. And as we know that acute cardiac events following by the rupture of unstable plaque are the leading cause of the death and disability in the developed world. And to identify this unstable plaque, it requires both structure and composition of the artery wall. And then combine the photoacoustic and iris imaging is really a great tool for that. As you can see, the iris imaging can nicely provide the structural information, and the co-registered photoacoustic imaging can image different tissue types based on the optical absorption contrast. As you see here, the photoacoustic imaging is tuned itself to aiming to image the lipids, which is a really important component inside plaque and used as a marker to identify this plaque. So you see here the bright signal is generated by the lipids. So by combining these two images, we get both structure and composition information of the artery wall. And if you compare this with the histology result, this is a lipid stain, ORO staining. So lipids are showing in red. And we see in photoacoustic signal, we pick up the lipids around the lumen very well. And generally speaking, the caster for this combined imaging system mainly consists of ultrasound transducer plus optical fiber. And to guarantee a nice iris imaging, normally a transducer with the central frequency higher than 20 MHz is used. The question is that also a good choice for photoacoustic imaging? To answer this question, we start a study on human coronary artery samples. This is the setup. We have a 400 micrometer forward-looking optical probe to deliver the light, and we place the transducer at the optic side, and we combine two transducers to cover a relatively wide frequency band, receiving range. And one is from 1 to 20 MHz. We refer to it as a low frequency probe, and the other is from 10 to 35. We call it a middle frequency transducer. And for comparison, we also include the data from a high frequency transducer as we published before. And this high frequency transducer is from 30 to 50 MHz. And a tissue holder with an open window sized 5 times 5 millimeter was designed to hold the sample, and it connected with the 3D moving stage to scan the sample. And before we mount the sample in, we do the OCT imaging to exclude all the healthy artery and then locate the plaque area. And in the end, 7 coronary arteries with 36 image locations were included in our study. And then we cut the artery open longitudinally and mounted in this setup. And we performed the spectroscopy photoacoustic imaging from 1125 to 1250 nanometer with 2 nanometers gap. So during the measurement, we shine the laser light from the plaque side, and then we receive the signal from the other side. Then this is a typical RF time trace we got, and then we can easily separate the signal from the plaque, generated from the plaque, and then we isolate this part of signal and then perform the Fourier transform on this part of signal and to analyze its frequency content. Then by combining the data from both low frequency and middle frequency transducer, we got the frequency content in a wide frequency band. And clearly to see most of the photoacoustic energy of plaque is below iris frequency band. Say 80% of the photoacoustic energy is even below 4.5 MHz. So if we covering the low frequency part, the SNR can be increased by 20 dB. With the same way we process all the data we have, then we get this statistic result. As we can see here, 60% of photoacoustic power of plaque is below 6 MHz, and 80% of the photoacoustic power is below 8 MHz, except for 2 outliers. So next, let's see about the optical spectrum of this plaque at different frequency band. This is a typical spectroscopy photoacoustic depth profile. You can see different spectrum at different depths. So by looking at this spectrum, you can already see come from different tissue type. It also confirmed by the histology, like what you see. This part is from the adipose tissue. It's giving a spectrum like this. And then this part is from plaque, and it's given a spectrum like this at a different frequency band. I think you already noticed that. The photoacoustic spectrum of plaque changes at different frequency band, especially at low frequency. It's much wider than at middle and high frequency range. However, with the pure cholesterol sample, the cholesterol is one of the dominant lipids inside the plaque, so we use it to represent the plaque. And we see with this pure cholesterol sample, the spectrum is quite similar at different frequency range. So we think the reason why this plaque spectrum changed at low frequency range is because of the large special kernel with low frequency transducer. So we receive the signal from a mixing tissue type of lipids of other things like calcium and collagen, etc. And to characterize this spectrum change, we will look at the peak location and the full width of at the half maximum of the photoacoustic spectrum. And we can easily appreciate that for a spectrum of plaque, the peak location are hardly changed. However, the width are increased from around 50 nanometer at high frequency range up to 80 nanometer at the low frequency range. So back to the question we asked at the beginning. We know the answer now. It may not be optimal to use this high frequency transducer for photoacoustic imaging. However, we also want to keep this high resolution iris image. So to solve this problem, we propose this dual element photoacoustic and iris imaging caster. Our idea is to place a piece of low frequency PVDF transducer on top of a high frequency PCT element. And that's the common design with the current system. So by doing this way, we can increase the photoacoustic SNR while keeping the high resolution iris imaging. So now we are still working on this low frequency PVDF transducer. We know that for PVDF transducer, it has really low acoustic impedance and really outstanding broadband receiving performance. However, it has a really high electrical impedance. So we need to design an IC to match this impedance. Particularly, we need to adapt these things. To this intravascular application. So it needs to be as small as possible. And we have this single wire readout IC design. It's using single cable to power and read out the signal. This is the photograph of the prototype of this caster. And we also perform some tests to characterize the performance. In a table, it's the performance of the single wire readout IC. And these two figures are the property of the element. The up one is the output voltage against the pressure. So you can see the detectable minimal pressure for this element is around 30 Pascal. And the bottom one is the frequency response of this element. We see it has a really flat frequency response at from 2 to around 15 megahertz. So if you want to know more detail about this design, please attend this talk. It happened this morning at 11 o'clock at room 102. It will be presented by its designer, Chao Chen. So please attend that. And to conclude my study, we found that plaque lipid has 80% of its photoacoustic energy below 8 megahertz. And the SNR of photoacoustic image of plaque lipid is significantly increased by covering the low frequency range, especially below 8 megahertz. And the photoacoustic spectrum of plaque lipids changed in the low frequency range, and we think it could be caused by we receive the mixed tissue types. And the last thing is the low frequency sensitivity can be achieved by a highly sensitive and broadband PVDF miniature transducers. And I would like to thank all the people involved in my work and my founding, and thank you for your attention.